All right, so now that you've thought about it a little bit, it should make sense to you what we're proposing to do, namely weigh the rat and see, weigh the flab rat and see where it falls on this distribution. Now, your friend, one floor up, is doing similar experiment, similar study, except your friend didn't use this plus 100 diet, but your friend used she used a plus 50 diet. Now look what happens with the plus 50. You got some overlap that's going to cause some confusion here. You see, you've got some of the green weighing less than some of the red, or some of the red weighing more than some of the green. In fact, 7% of the green weigh less than this 5% of the red. So what would you do? Well, one idea might be to push our discriminator up here. If we push our discriminator up here, then we would get it right for all the reds. So if the flab rat actually came from the null distribution, it would never be classified as coming from the diet distribution. But if we had one of these that weighed 120 but came from this distribution, or one of these that weighed 130 and came from this distribution, how often does that happen? Well, it's 7 plus 12. 19% of the time, we would be misclassifying these guys as these guys. Okay? So, another way to do it is to shift the discriminator a little bit to the left, but now what we're going to do is pick up a little bit of the red. Now, 5% of the time, we'll be incorrect with the red because they will be classified as high to the right of the pen. And 7% of the time, we will be classifying the greens as reds, or the null. This is exactly what happens with hypothesis testing. So with hypothesis testing, if we have the cutoff at 125, when the new mean is 150, then our alpha is 0.05. That means 5% of the time, flab rat actually comes from the null distribution. We will be misclassifying them. So there they are. That's the 5%. There's your alpha of 5%. And your beta of 7% are these guys, who actually come from the green, but because they're to the left of the arrow, will be classified as the nulls. So, of course, 1 minus beta is the power. So we have 93% power. What we say is we have 93% power of distinguishing between the null distribution and the plus 50 diet. Your friend 2 floors up is doing yet another experiment, another study, yet another study. He is using a plus 40 diet. So the mean of that distribution is 140. Now you're seeing a bigger overlap. So if you're keeping your cutoff at 120, why would you do that? 125, sorry. Why would you do that? So that you have this 5% here. Now you understand why I created these with 5%, so that you would always have an alpha of 5%, which is what we always do. All right? Now, if you keep the cutoff here at 5%, you will be doing the wrong thing by the green ones here and the green ones here. The green ones that weigh 110 and the green ones that weigh 120. There's 7% there and 12% there. So now your beta goes up to 19% and your power goes down to 0.81. I'm going to be sending you off to doing a demo on your own. But it's not as complex as this. What we've done is we've idealized the demo. Instead of having a bar chart like this, we've said, okay, suppose we have a continuous version. So here's the continuous version of what we've been talking about. So this would be the case when we did the plus 100. So you can see the mean here is at 200. Okay? Now you also see that with the idealization, there's an itsy bitty of overlap even in this case. So now this would be the plus 100. This would be the plus See, now the mean is at 150, so this would be the plus 50 diet, and you can see you've got this much overlap at the plus 50, and then at this would be the plus 140, because the mean is actually at 140 here, is the mean. And now you can see much more overlap. So if we always keep our bar here to be such that this is 5%, then you can see that you capture a lot more area here under the green curve when it's plus 40 than you would when it's plus 50 if we have it like that. So see if you can convince yourself of this finding by using the demo.